Hello, this recording is about the second classical technique, support vector machines. Support vector machines, or SVM, are very powerful and versatile machine learning models. They are capable of performing linear or non-linear classification, regression, and outlier detection. They are well suited for classification of complex but small or medium-sized data sets. Complex means many features but small number or medium number of samples. SVM is an excellent model because it gives large margin classification. Here are some examples to explain its concept. Now, assume that we have two classes, yellow and blue, and we have two features, petal length and petal width, and we're searching for a decision surface that separates the two classes. This one is not good because there are yellow and blue from the left. This one is okay. It separates the blue from yellow. This one also is okay because it separates yellow from one side and blue on the other side. But SVM gives large margin classification. It gives better decision boundary, like this one. This boundary maximizes the margin between the two classes. The decision boundary in SVM is fully determined by the instances located on the edge. These instances are called the support vectors. These instances on the boundary are called support vector, and the decision boundary is determined only by these support vectors. It is not affected by the other far samples. SVMs are also sensitive to the feature scales. Here we have one example. We have two features. The scale of x1 is much larger, about 10 times the scale of x0, here in tens and here in units. With these samples, we get this decision boundary. Now, when we scale the features, we scale them around 0, we get a different decision boundary, and this is better because the margin is larger. The basic SVM is hard margin SVM. For classification, this is hard margin classification. Hard margin classification means that there cannot be samples or instances in the margin. Hard margin classification cannot handle linearly inseparable classes like this one. Here we have an outlier, a yellow instance inside the blue ones, so there is no linear boundary that perfectly separates the two classes. Also, hard margin classification is sensitive to outliers. For example, the yellow has one outlier here, and this pushes the decision boundary close to the yellow. So it is the margin now here is very narrow. The current solution is to use soft margin classification, which finds a balance between keeping the margin as large as possible and limiting the margin violations. In the soft margin classification, you can have some violations inside the boundary. Here is an example. This is the decision boundary, and between the dashed lines is the margin, and there are some green in this side and some yellow on the other side. In SVM, you can control the number of violations, the number of instances inside the margin using a special parameter called the C hyperparameter. Here, C is small and the margin is wide and the violations are many. When C is increased, the margin decreases and the violations, number of violations decrease. Usually, if you have overfitting, then use smaller C, and if you have underfitting, use larger C. If your SVM model is overfitting, you can try regularizing it by reducing C. Now, I'd like to describe an important dataset, which is the IRIS dataset. It is a famous dataset that contains 4 features, which are the sepal and petal length and width of iris flowers. There are 3 classes: the setosa iris, the versicolor iris, and the virginica iris. Scikit-learn support this dataset. You can import it by executing load iris function from datasets, and you get an object here, which is a dictionary that contains the data, the features, the target or the labels, and other things. Here is a complete SVM classification example. From scikit-learn, we import datasets, and here we use load iris to load the dataset into the object or dictionary iris. Then for features, there are 4 features, but we will concentrate on the last 2 features, feature 2 and feature 3, which are the petal length and width. So we take all instances, 150, and we take feature 2 and 3. For the target, we have 3 labels, 0, 1, and 2. 2 is the label for virginica iris flowers, and we want now to have a binary classifier. So the labels here are 0 or 1, 0 if not virginica, and 1 for virginica. Here we use the linear SVM classifier, also available from scikit-learn, and usually we start with C hyperparameter equals 1. We can increase it or decrease it if we have overfitting or underfitting. The loss function is usually hinge, which is used for maximum margin classification. Notice that we have the SVM classifier, the linear SVM classifier in a pipeline with the standard scaler. Standard scaler scales the features, then the classifier does the classification. For training, as usual, from this object, from this model, we call fit on the data and the labels. This will execute for some time. Then we can use this model to predict. Here the example is one sample and it gives one. This means that from this feature, two features, it predicts that it is true, it is Virginica. Also, there is nonlinear SVM classification. The SVM class from scikit-learn supports nonlinear classification using the kernel option. Using the kernel option, you can specify the type of nonlinear classification you want to do. Here in this example, we select a polynomial nonlinear classification. The polynomial here is of degree 3. Again, the classifier with the standard scalar are in one pipeline. We do fitting as usual. Here we also have the coefficient 0 parameter, which is used to control how much the model is influenced by high degree polynomials versus the low degree. With the larger numbers, the model is affected more with high order terms in the polynomial. This is the C parameter, and here we have two models. This model is degree 3 and this model is degree 10 with higher coefficient 0 value. Here we have more elaborated model. Here we have a less elaborated model. Usually you go to a higher degree if your model is underfitting, and you go to lower degrees if you have overfitting. Another kernel usually used in SVM is the Gaussian radial basis function. The Gaussian RBF is usually calculated using the exponent of negative constant multiplied by the distance of the features from some point. Here we have an example. RBF can be used to find similarity features, like here we have point at L equals -2 and here at L equals 1. This problem is initially one-dimensional problem. It's hard to classify because linearly, because the green comes between the blue. We can transform it using RBF into transform x1 to x2 and x3, and x1 and which is -2 in this case and 1 can be used here to get these two features. Now when we transform x1 to x2 and x3 using the RBF, we get two-dimensional problem. Now there is a decision boundary that separates the green from red. Here how we use the RBF kernel in this pipeline using the SV classifier class. We use the RBF kernel. It has hyperparameter gamma and C. The RBF kernel transforms a training set of M instances and N features to M instances and M features. We'll have features as many as there are instances, because there is an RBF feature for each instance. The gamma and C hyperparameters are used for regularization with the smaller values. If you have overfitting, then choose smaller gamma and C. Here we have the Gaussian RBF kernel with gamma equals 5 and C 0.001. Now going to smaller gamma gives a simpler model. Also going to smaller C gives a smaller model. Here with large gamma and large C we have very detailed, maybe overfitting model, and this is underfitting. Now to regression. Also SVM has linear and nonlinear regression. The linear SVM regression fits as many instances as possible on the margin while limiting margin violations. It tries to have as many instances inside the margin and minimize the instances outside the margin. These are called violations. The width of the street or the margin is controlled by a hyperparameter epsilon. So this is epsilon 1.5, large street, large margin. This is epsilon 0.5, smaller margin. And this is how you use it. Import linear SVR for regression from SVM collection of scikit-learn. Here we create a model from linear SVR with epsilon 1.5. This is for this case, and this is how we fit it. For the also there are nonlinear SVM regression, and you use the SVR class with, for example, kernel equals polynomial. Here we're trying to fit these samples with a polynomial of degree 2. C hyperparameter is 100, epsilon is 0.1 here. Now this is with C as large as 100. The model is trying its best to fit these points. Now with the smaller C, it does not try that hard, and we have more violations here. To summarize, in general, SVM models are very powerful. The linear SV classifier has complexity of order m by n, m number of instances and n number of features. But the SVC with nonlinear classification models, it has a time complexity. Its time complexity is usually between order m squared multiplied by n and order m cubed multiplied by n. So it takes a lot of time if you have many instances. So in conclusion, the algorithm is perfect for complex, means many n, many features, but small or medium training sets. However, it scales well with the number of features. This is the end of this recording.